So the last talk today is from Larry Zitnik, who, amongst his many other distinctions, has the distinction of not being a faculty fellow. This is because he actually works for Microsoft as a senior researcher. And he's an expert on stereo vision and has done some highly original work on object recognition. In fact, the wisdom of the crowd suggested to me, this is unofficial, that his was one of the very most interesting papers at CVPR a couple of weeks ago, doing some rather bold, a rather bold attack on object recognition. I'm not sure if that's what he's going to tell us about now. It is, so I'm very much looking forward to hearing it, Larry. Thanks.
All right, you can hear me? Yes, okay. Great. So today I'm going to be talking about common sense. So what is common sense? Common sense is knowledge that we all have. It's knowledge that we assume other people know about the world, right? And the problem is that us as computer science researchers is that we have common sense, but our computers don't. And this is really limiting our ability to reach the research goals that we want to achieve. Now, what I want to start off with is give you some idea from my own field, which is computer vision, as to how common sense can help our field and also how it's hindering further research in computer vision. So about 10 years ago, context was one of the big notions in computer science. And the idea of context is we don't want to detect objects in isolation. We know that people walk on the ground. We know that cars drive on roads. We know that buildings are perpendicular to the road, etc. This is all knowledge that is common sense. If we can encode it into our algorithms, then we know that detecting a person up in the sky must be incorrect. More recently, what's been getting more attention is attributes. So we want to label attributes of objects and scenes. So for instance, here you have what we would say is a rough texture on the left-hand side. So we recognize this as grass, and we say that looks pretty rough. We know long grass is rough. And on the right-hand side, we see, let's say, it looks like a carpet. And we say we felt that it'd probably feel pretty furry. And as humans, we do this attribute labeling by recognizing what these objects are, that this is grass and that's carpet. And if we just change the color of these two objects, then we suddenly attribute these images to completely different objects. So now this looks like fur of a dog, and that looks like astroturf on a field. And then our knowledge, our intuition as to whether these are furry or rough completely switches. And this is different than what a computer vision algorithm would do, which is just looking essentially at the texture of the object without doing object-level reasoning. It becomes even more apparent sometimes when you think about scene-level attributes. So some scene attributes are pretty standard. They're like, is this a forested scene, or is this a city scene? Things like that. But some of the attributes that we're trying to learn as a community are things such as diving. How are we going to learn the difference between the left-hand scene and the right-hand scene? Which one is more likely to be good for diving? Right? That takes a lot of common sense knowledge to know which one of these is more applicable. Common sense knowledge also tells us which images are unique, which ones are interesting, which ones we actually want to look at. And this tells us the difference between what images are just funny to look at, which ones are just silly images. Common sense knowledge can even tell us what somebody is doing. So you look at this guy up here. What is he doing? He's standing up, sitting down, doing some weird yoga pose. Kind of hard to tell. But if we look at the whole image, we know obviously that he's not just sitting down, right? He's booking it out of there. He's running away. He's afraid of the bear. Now, common sense knowledge is even more important when we start thinking about semantically describing scenes. So for instance, here we have two birds have funny blue feet, or two birds with funny blue feet, right? We wouldn't say that they have funny orange feet if they had orange feet, because most birds have orange feet. It's not unique. It's not new. But they have blue feet, which is really unusual, which our common sense knowledge is telling us. Therefore, we should describe it. Now, this is a fairly simple example of using common sense knowledge in semantic description, but let's look at this image here. Now, this is just a simple image, just two people standing in front of a blackboard, right? And an easy description would be two professors converse in front of a blackboard. Now, let's talk about what knowledge we actually need to understand to come up with this description. First, we need to know that they're professors. How do we know that they're professors? Well, they have receding hairlines, which means that they're older. It's a good sign. They look distinguished. They have suits on. Older people that are distinguished, good sign they might be professors. But there's also businessmen that are also older and distinguished. They could be businessmen. The true giveaway here is that they're standing in front of a blackboard. And how do we know it's a blackboard? Well, it's a black wall with chalk-written equations on it. Right? So we know that if you're an older person that looks distinguished, standing in front of a blackboard with chalk, you're probably a professor. Now let's look at the word converse. Converse is an interesting word as well, because converse means that you're talking about something intelligent. Right? They're not talking, they're not chatting. If these are two students, they'd just be chatting, right? But no, they're conversing. Why are they conversing? Well, professors talk about intelligent things, right? So therefore, they have to be conversing. And not only that, they're standing in front of a blackboard with really complex equations in front of it, right? So obviously, they have to be talking about something intelligent. Therefore, they're conversing and not talking and not chatting. All right. So as you can see, as computer vision, as we start trying to verbally describe our images, as we're trying to incorporate semantics into computer vision, we're essentially pushing the field closer and closer to AI. Because without AI knowledge, without common sense knowledge, a lot of these tasks are infeasible, or infeasible to do to the level of detail that we want to do them. So why is something so common so hard to find? Why is it so hard for us to get common sense knowledge inside of our computers? And to examine this, let me just do a really quick case study. Let's try to answer the question of why a bird flies, or does a bird fly? Right? So if you're before the internet age and you grew up a while ago, you might say, well, let's look it up in a dictionary. And if you looked up bird in a dictionary, what would you find? A bird is a feathered animal. You ask a 3-year-old what a bird is, and the 3-year-old would say, it's a flying animal, something that flies. Yet the dictionary never even mentions it's a flying animal. Now, if you're really smart and you were a computer, maybe you could look up in all of the dictionary and try to find all the entries which have the word bird in them. And you could find an entry that looks like this. Penguin, a seabird that doesn't fly. Right? So then you can deduce from that, okay, so a penguin is a bird that doesn't fly, so therefore most birds should fly. But this is a seabird. So is a seabird the same thing as a bird? It gets confusing, right? Okay, so that's for the older people in the audience. Now, for the younger people, you'd say, well, nobody uses dictionaries anyway. They're out of date. They don't tell you what you want to know anyway. Look it up on Wikipedia. Wikipedia has everything. Wikipedia will tell you the right answer. Well, if we do that, we find this. 2 paragraphs. Middle of the second paragraph, it finally tells you that most bird species can fly. Right? I mean, this is after, that they've been around 150 million years, that a hummingbird is a small bird, and an ostrich is a larger bird. All this other minute trivia that nobody cares about. Really, what you want to know is that they can just fly. And you don't even mention that at the very beginning. All right. So Wikipedia, maybe not as useful as either. So what if we just do web search? What if we just do web search for flightless bird and flying bird? What do we get? Then you get something like this. Flightless bird shows up 48% of the time, and flying bird shows up 52% of the time. So you might think about, okay, about half of birds fly, right? But this, again, is incorrect. And the reason for this is actually a very simple reason, is that if you are describing a bird that is flying, you don't bother mentioning that it's a flying bird. We already know that birds are flying. There's no reason to actually talk about this. The only thing that's worth actually talking about is when a bird is flightless. Therefore, there's this bias to mention things that are unlikely to, or unusual. Therefore, you see flightless occurring almost as frequently as flying. So another attempt to learn common sense knowledge is the Psych project. This has been going on for about 30 years, headed by DonڳÇÖt from University of Texas, I believe. And he has a company now called Psycorps, where they're hand-coding in all these different sources of information, such as bird is a flying animal. And they're doing most of this manually, but a lot of it's also automatic as well. But I think most of us in the room here would agree that that's kind of a brute force, not the ideal way of actually learning common sense knowledge, even though right now it is probably the most effective way of doing it. So how do we as humans know how do we as humans know that birds fly? You know, it's so obvious to us. It's so obvious to a 3-year-old that birds fly. Why is it so obvious to us? Well, we see birds flying every day. We observe it. It's part of our reality. There's birds everywhere. We always see them fly. This is like just trivial, right? So why can't we just have computers do the same thing? Why can't we have cameras everywhere? Why can't we have robots walking around the world, just observing the world and realizing, hey, I've seen birds, I've seen them fly, I know they're flying, I know almost all birds fly. It seems trivial, right? So why can't we do this? Well, the reason is simple, and it goes back to Feifei's talk. It doesn't work. Object recognition doesn't work. Okay, it works kind of. It works all right. But for me, working at Microsoft, a product group comes to you and says, I have this great app, and all I need to do is, recognize this person, whether they have a feathered cap on, and how many fingers they're holding up, and they have to be wait. Sorry, it doesn't work that well. Yeah, we have papers that kind of show good results, but don't pay attention to that. It doesn't really, in real world, it doesn't really work as well as you might think, and that's unfortunate, But that's the reality right now. Is that we just can't observe real-world data, and the object recognizers, they work kind of, but they don't work as well as we want them to do. So what can we do? How can we actually get this common sense knowledge? We can't observe it like humans do. It's too hard mining the web. How can we gain common sense knowledge about our world? All right. It's kind of depressing, but let's just forget about that for 1 second, and let me just show you a quick video. Now, this is a video that was made in 1944 by two psychologists at MIT, Heider and Simmel. Later uploaded to YouTube. You can watch it there. And it's just about a minute long. I'll just let you watch it. Scary, isn't it? That poor little circle. So what's amazing about this video? What's amazing about it is it's a circle and two triangles. Yet it had very deep and rich semantic meaning. We all sat there. We were worried about that little circle. Why was that big triangle so mean? Right? And thankfully, that little triangle was there to help out that little circle. We all had the same thoughts. Now, our interpretation of the circles and triangles might be different. Some of you might have thought of the circle as a baby, some of you as a woman, some of you as a bird, etc. But our understanding of what was going on is all the same. And this is very simple visual phenomena that can arise and create very complex meaning to us as humans. Now, this shouldn't be too surprising to any of us in the room, especially anybody who is being a kid. We observe this all the time when we watch cartoons. Right? We can have, very simple visual phenomena, yet it's very interesting what's going on. There's a lot of common sense knowledge that we can glean from these visually very simplistic images. So for instance here, with The Simpsons, we could learn, let's say we just learn common sense knowledge from The Simpsons. We could learn that most people sit in front of their TVs lying on a couch. Right? We could learn that lamps sit on top of tables, that picture frame is slightly crooked most of the time, that moms generally have blue hair that's really tall, etc. Right? And you can think maybe computer vision would actually work on these images. Maybe we could actually recognize these things. So it is so much simpler. Imagine we could have a computer that we're learning all this common sense knowledge from The Simpsons. It'd be like aliens coming to our world, and all they would know about our world is The Simpsons, and then you'd have to communicate with them. It'd be like hilarious, right? Now, I'm only kind of half joking here. And what I think is interesting, and what I think the question that this raises, which I think is interesting, is that is photorealism necessary? If we want to gain common sense knowledge about the world, if we want to semantically be able to describe our world, do we actually need to start with real images? Could we instead start with cartoon images, something simpler, something in which the computer vision problem is solved? Can we get around this whole object recognition problem? And that's a question I'm going to talk about for the rest of this talk. So in order to study this problem, we created our own cartoon starring Mike and Jenny, two children who can play with all sorts of different objects. They have different balls they can play with, different animals they can play with, trees, playground equipment, etc. And what we're going to do is we're going to have and also, since we're modeling children, we wanted to be able to study their expression changes and poses and whatnot. So we have all different sorts of poses and all different types of expressions. And what we're going to do is we're going to have mechanical Turkers come in and generate tons of abstract scenes or cartoon scenes using a mechanical Turk interface such as this one. So basically the Turkers can drag and drop the clip art in. They can flip the clip art left and right. They can make it different sizes and basically arrange it as they please. We don't constrain where they can put clip art at all. So they're allowed to do whatever they want. We do ask them to create realistic clip art, so hopefully it's not too out there. So what's interesting is we can have a scene such as this, But we know exactly where all the pieces of clip art are, because we have that information. And not only that, we also know the gaze of the children. We know the pose that they're in. We know whether they're smiling or crying. We know if there's a cloud up in the sky. We know all this information. This is actually very rich visual information, much richer than is easily gotten from real images. And there's a lot of information. We know the co-occurrence. We know whether two objects, whether they're facing each other, their relative positions, etc. There's a lot of very rich visual features that we can glean just from this simple annotation here. So you can imagine some of the things that we can learn. We could learn that children are unhappy when it starts raining outside. We could learn that children are actually happier when they have balloons and they're standing in a playground. We could learn that children get upset when snakes chase them. We can learn that when you go camping that you typically build a fire. You can learn that Mike is generally affected by Jenny's state. So there's all these kind of interesting, kind of common, like duh type things that we can learn just by observing these cartoons. Now, if we're going to learn common sense knowledge, we want to be able to express this knowledge as well. So we want to be able to relate it to some sort of semantic meaning. So to do this, what we do is we create a whole set of scenes like these, but then we also ask another set of Turkers to come in and then write written descriptions describing those scenes. So here you have Jenny loves to play soccer, but she's worried that Mike will kick the ball too hard. And this is very similar to a large body of work that's out there in which people are relating real images to sentences and also real images to just keywords. And basically in the last 3 or 4 years, this has been a really hot topic. And basically, this is basically doing the same thing, except for now we have nicely annotated abstract scenes. But there's something you can do with abstract scenes that you can't do with real images, which I think is really cool. And that's the following. You can take an abstract scene, you can ask a Turker then to generate a written description of that scene, and then you can do one more thing. You can take that written description and then ask a set of other Turkers to generate scenes depicting that written description. So we can basically create a whole set of clipart images depicting the exact same sentence. So let's look at this. So here we have a sentence. Mike fights off a bear by giving him a hot dog while Jenny runs away. What's amazing about these scenes is how different they are, yet they all convey the exact same semantic meaning. They all have Mike sitting there holding a hot dog up to the bear. Mike, and a lot of them, is looking kind of, not very happy about giving up his hot dog. Jenny's running away in the opposite direction. But, the trees vary. There's a picnic table in some. There's a grill in one. There's a hot air balloon in the other. There's so much variation in these. It's interesting because we can actually learn what the essence of, let's say, giving a hot dog implies. Here's another example where it was raining in the park and the duck and the snake were trying to take shelter. And what's interesting here is look at the different types of shelter. We could learn that tents, picnic tables, trees, they all can offer shelter. Just from these different images. Now, some of the sentences that we have are very specific, like the two I just showed you. Other sentences have a tendency to be a little bit more vague. So here are 6 images. Can you guess what the written description for these 6 images are? Any ideas? So you might be guessing that the written description here is actually Jenny and Mike are both playing dangerously in the park. I mean, just look at the way that the Turker is coming up with creative ways of Mike and Jenny being able to play dangerously in the park. You have Mike sitting there throwing a ball at a bear. Not a good idea. Jenny running up the slide. Mike playing with a rocket ship. Jenny kicking a snake. All these different ways that you can be creatively dangerous in a park. It's just like real kids. There's so many ways you can get in trouble. So the data set we created is essentially 1,000 sentences, and we then generated 10 scenes per sentence for a total of 10,000 scenes. And you can think of each of these sets of 10 sentences as a class, a semantic class of of scenes which had the same semantic meaning. And we can use this data set to do a lot of interesting things. Now I'm just going to go through a couple works that are just recently done, or works in progress, and works that we're hoping to do in the future. So one thing that we did, which is very simple, is just study the mutual information between the visual features and the semantic classes and the visual features in the words. So we can learn which words are semantically meaningful, which visual features are actually semantically meaningful. So for instance, we can learn which objects are most likely to be talked about in a sentence. So for instance, these are the objects that are most semantically relevant. You have the bear, you have Jenny, Mike, the cat, the dog. If a bear appears in an image, you're going to be talking about it. Now on the flip side, things that aren't very relevant, hats that children can wear, pails, tennis. Obviously, tennis isn't nearly as cool as soccer. Ketchup, mustard, those sort of things. If they appear on the scene, they're probably not going to be talked about. Something I think is really interesting is this data set. It can be really fine-grained. We can learn subtle differences in meaning. For instance, Jenny ran after Mike, and Jenny ran to Mike. Right? You might think that they're very similar, right? But they actually, if you think about the image that pops into your head when you think about running after somebody rather than running to somebody, it's subtly different. And both of them, Jenny's going to be in the running pose going towards Mike, right? But Mike's going to change. If you're running after Mike, that means Mike is also running in the same direction. And if you're running to Mike, Mike can just be standing there in any pose looking in any different way. And this is the type of information that we can actually learn. And we've been able to take sentences such as these and then generate scenes depicting them and have them accurate to this kind of level. And here are some of the relationships that we've learned. Now, there's over 400 different relations that we've learned, and this is just a kind of a quick snapshot. So we have, running away from, run towards, and you can see the relative position of the objects relative to each other. We can also study which words are actually visually meaningful. So not too surprisingly, nouns are actually visually very meaningful. And this is good news for the computer vision community because we've spent almost all our time investigating nouns. But second up is verbs, followed by prepositions. And prepositions tell us a lot about relative positions of objects relative to each other. And then followed by adverbs. If we look at which words are least visually informative, we get these words here. And one thing that's interesting is a lot of words that have to do with temporal information have very low ranking. So like before, during, today. And this is partially an artifact of our data set, in that our data set is it's just static scenes, right? So this is, on this topic, this is something that we've actually begun to look into. So we've been thinking about, can we actually create stories using mechanical Turkers? So we have Turkers then create sequences of scenes that go together. So here's an example that we got from Mechanical Turk. We have Mike here holding a snake, trying to scare Jenny. Jenny gets scared, she drops her Coke. Jenny runs away, Mike's happy, I got rid of the girl. Little does Mike know, though, that there's a bear standing behind him as he's walking away. He notices the bear, gets frightened, his hat flies off, and the snake goes flying. I mean, think about it. Clip art could tell us about it could inform us what karma is in the world, right? I mean, we could learn all these kind of subtle things. We can learn causal relationships. We can learn what makes people happy, which makes people sad. What are the different relationships that take place through time? And I think this is a really interesting aspect of this work and how to examine how we expect the world to kind of evolve through time. So I'm going to close on just a few topics. When I discuss this idea of using clip art and learning about the visual world through it in abstract scenes, I often get very similar questions, and I just wanted to address a couple of them right now. And one of the things that I think is important for this sort of task is to make it fun. Because one thing that we found is that Turkers, when they do this task, they love doing it. It's almost like a game for them. You see posts on the web where they basically say, I've been Turking all day, I finally made my $15, and now I'm going to reward myself by doing some Jenny and Mike tasks. And what's great about this is you don't have to pay them as much, right? You can get away with, paying them like a third of what you'd have to do if it was a really boring task. Because I think many of us, when we think of Mechanical Turk, we're like, it doesn't matter, it can be completely boring, we're paying them to do it, they'll do it anyway. But the reality is, if you make it fun, then it's kind of halfway between a game and halfway between a true Mechanical Turking task. So you don't have to pay as much, but you don't have to go to the level, if you're actually creating a game, to get it to that level of detail and refinement that people actually just want to play it for free. So it's a nice balance. The second thing is realism. So all of the work that I showed you today, you might say, well, how much does this actually really apply to the real world, to real images? Because, I mean, the clip art I showed you is very cartoony. It's just kids. They don't look like real kids. A lot of there's bears running around with their hands up in the air all the time. So, and a lot of that is a legitimate criticism. But the reality of it, though, is I think the methodology can actually be expanded to really include more realism. So right now what we're doing is we're creating a much larger set of clip art, which looks more real, and also has much more variety in it. So we can learn a much more rich and diverse set of interactions that exist in the world. Another question I get is 3D. Why, I mean, we basically only allow mechanical Turkers to do very limited sets of interactions. They can basically flip an object left and right and make it different sizes. Why don't we let them, basically, why don't we go to SketchUp and find 3D models online and allow Turkers to kind of rotate things left and right? Well, that again gets back to the fun aspect. Turkers don't enjoy that. It takes a lot of tedium out. It makes the task very tedious. So we didn't really want to go to true 3D. And then finally, relevancy. So here, we have the bear, right? And it's like scaring the children. You might think, well, is this really useful at all? All we're learning is that bears chase children, right? But the reality is, you look at the scene, there's a lot more going on in it. There's the hamburger and the pizza are sitting on top of the table. There's a grill. We can learn that children like to stand by campfires. And the bear just happens to be there. The bear, again, is important because it makes a task fun. The Turkers like to do it. But still, you learn all this other common sense knowledge about the world. And the other important point is we only show a small subset of the clip art to each Turker. So our data set, while I'm showing you a lot of bears today, only contains a small fraction of actual bears in the data set. All right. So just to conclude, this is basically a new way of learning common sense knowledge about the world. If you think an image is worth 10,000 words or something like that, I'd say an abstract scene maybe is worth 100. It's a nice high bandwidth way to have mechanical Turkers, everyday people, just give us common sense knowledge about the world. And one of the great things is now we don't have to wait for object recognition to actually work, to start studying these areas, to start studying high-level semantics, to start studying how can we glean common sense knowledge about the world. So let me just conclude by thanking two of my collaborators. One is Devi, which is sitting right there, and Lucy, who's also at MSR. Thanks.
Thanks. Great talk. Time for a quick question over there at the back.
Have you considered using this at the psychiatric domain, like, for example, autism, where the gist is not actually the same as how the normal we see it, and use this as a rehab tool or getting the classification and say, all right, these are the deficiencies that they have?
It's a good idea. This work is just brand new. We just presented it for the very first time weeks ago. So we have been getting some very interesting questions along those regards. They're just studying, what do people find salient? What do people find memorable? And those sort of questions. So I think there is some definite potential in psychology and human psychology and studying those different aspects and using it as a treatment device. Yeah.
One more question. Yeah.
Did you do the reverse, showing the scene, but asking for alternative descriptions of the same scene?
So we have done like the telephone game, where you take a scene, you get multiple descriptions of it, and then you have people then generate multiple scenes of that and see if it diverges.
Yeah, like Bill Dolan is doing for paraphrase detection,
Yeah. So
perfect.
We have a couple different data sets. Some we have for a given image, we could then have 6 different sentences describing it. And then we also have, for a sentence here, 10 different scenes that depict that sentence. And all of this, what's great about it, is so cheap. For $300, we can get 30,000 sentences. So scaling the data set up and doing these different things is so easy to do.
Great. Well, thanks very much. Thanks very much to all 3 of the speakers for the afternoon. Let's thank them for some great talks. You get your coffee break now, but do come back after the break. Rick Zaliski is chairing the second session on computer vision.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.